Good evening, everybody, and thanks for attending the full day of PEC program. And also good morning, because we have some attendees joining us from US, and also our next keynote speaker will come from US. Just to frame it in the program. So next is the keynote from Mike Mayberry. Then we do a closing session, and after that we can still have, let's say, a virtual beer at our experience room. Now for the next few minutes, it's a special honor for me to introduce Mike Mayberry to the keynote. After, if you think the keynotes from yesterday, we had Vicky Mitchell from ARM talking about DevOps, really interesting about software methodology. We had Moshe Salkberg from Various talking also about what hardware guys can learn from software, both very inspiring talks. This morning, if you could follow the session from Dr. Matthias Straub from Volkswagen, as he was outlining the architecture for the new car, bringing together the hardware and software world, talking a lot about virtual prototyping and enablement. Now the next hour or so, the discussion keynote is about the future of compute verification in the era of heterogeneous design. A few words about Mike. So Dr. Mike Mayberry is a Chief Technology Officer at the Intel Corporation. He's a Senior Vice President and General Manager of the Technology Development, where he's responsible for the research, development, and deployment of next generation silicon logic, packaging, and test technologies that will produce future Intel products. Since joining Intel in '84, really quite a while, as a process integration engineer, Mayberry has held a variety of positions. As part of the California Technology Development Team, he's developed EPROMs and flash logic wafer fabrication process. In '94, he moved to sort test technology development, responsible for roadmaps and development of test processes for the Intel microprocessors. In 2005, he moved to components research and was responsible for research to enable future processes options for Intel technology development. In 2015, Mike moved to the Intel Labs and became there responsible for Intel's product-driven research. In 2018, he moved to the Technology Development Group at Intel. Mike received his bachelor's degree in chemistry and mathematics from Midland College and his PhD in physical chemistry from the University of California, Berkeley. Thanks, Mike, for getting up early for us, and looking forward to your keynote.
Thank you. I'm trying to share here.
Yeah. Okay, looks good.
Does it show up? Okay.
Yes.
Always want to check before I start.
That's good. We can hear you well and everything prepared.
Well, thank you for the introduction. I want to talk this morning about the future of compute, which is kind of a generic talk that I've been doing, but with a little bit of a focus on what that means for verification. And I think it's safe to say there's a number of challenges, opportunities that we have here that are different than what we've had in the past. So let me start with a little bit of background in terms of what I might have talked about 10 years ago or so. These are example slides from about 10 years ago. On the left, talking about transistor scaling, novel materials, novel architectures for the transistor itself. On the right, talking again about materials, but also talking about the problem of interconnects, the move to 3D design. The integration of new architectures and materials has really been going on for the last 15 years, maybe the last 20 years, depending on where you start counting. But one of the things that's missing from this particular page is a deep discussion around the implications of design. And so that is an important part that we take for granted, certainly during the era of Dennard scaling, where you just made everything smaller and everything got better. it was possible to at least fudge over the details. But clearly going forward, that is not the way that we can treat things. So we need to look at how we design the processes from a design rule point of view and figure out how that is embodied in the form of a standard library and in terms of an architecture. And then what does the IP look like at a full block level? What we're increasingly finding is that small differences in choices you make at the design rule level have a really big impact on what the full chip goodness will be. That's not gone unnoticed with others as well. The chart on the right is from TSMC, showing in this case, the amount of density scaling has been largely driven by process on the left, but is increasingly driven by a combination of process and optimization with the design on the right. And going forward, they expect this to be roughly a 50-50 trade-off. So half of it from essentially the process goodness and about half of it from getting better optimization with the design. This is a fundamental change from the way that we've done things before and has implications for how we do business going forward. Of course, with Moore's law, we have added complexity. Obviously, the design complexity goes up with the number of transistors or interconnects that you embody in the system. That in turn increases the amount of workload required from an EDA point of view. And the number of compute required goes up as well. Now you can see these multipliers are all roughly equivalent to one another, which says that compute is keeping up with the problem of design just barely. Obviously, that is both the challenge of Moore's law, more complexity, and the benefit of Moore's law, bringing more complexity to bear on the particular problem. So modern compute infrastructure is certainly required for doing design going forward. So what's the fundamental change that's going on in the world that leads us to the notion of heterogeneous design? Well, fundamentally, the nature of software is changing. We're doing fundamentally different workloads that are not suited to the architectures that we necessarily have been working and optimizing for the last couple of decades. Data is really everywhere, and it's increasing exponentially. Data by itself is not particularly useful, but data turned into information and information into decisions is useful. And so the ability to collect data, process it, turn it into information that we can act on is the important part of it. So if I look at some trends over a couple of decades, some things emerge. So I'll start at the upper left of the graph here. The light blue section is really productivity data. Think of spreadsheets, banking information, databases, things of that nature. You can see that was really what was leading the era of compute in the 90s, but certainly has shrunk as a portion of the total throughout that particular decade. In the middle is really entertainment. The middle blue section is broadcast data. This was accelerated with the move to digital rather than analog recording. It is typically centrally created and then distributed without modification to the edge. But the slice at the lower right is the rapidly growing one. So calling attention to this is both client-generated data. Think about the things that your cell phone collects, whether you snap a photo, you take a video, or simply the metadata, the location that you're at, what you're looking at on the screen when certain things happen. That metadata is labeled there. And then finally, too small to read really is the machine-to-machine data, where it never goes through the hands of a human being. All of those three things are what we refer to as unstructured data. They're typically not tagged very well. They're often in raw form. And really, the rise of AI has been driven by the need to understand that vast quantity of data. And the data is everywhere. The data is not just at the edge where it's collected, but it is moved around. Social media is one example. It is acted on, for example, figuring out what kind of targeted advertising you want to do. And what we see is processing unstructured data is fundamentally different from a compute workload point of view. And we refer to that generically as an XPU, as a processing unit to address the diverse set of unstructured data. And an X means more than one. It's not a single architecture that's optimal. Further, the compute required to do this is often embedded throughout the cloud, network, and edge. And that is both from a standpoint of being able to handle the data where it is most numerous, but also to manage quality of service and security things along the way. I made the point earlier that it's really not about data, it's really about turning data into information. And I illustrate that here with an automated driving example. Starting on the left, let's set out to build an automated car. You need cameras, you need other sensors, you need processing units to make sense of that. You need a way to feed maps into the system. All of those hardware solutions are just a starting point, the starting investment. Now, to take advantage of this, perhaps you build a service around it, a robo taxi, for example. Now, the value of the service is actually now more valuable than the hardware. And having put these out and deployed them on the streets, you realize you're collecting data along the way in real time that you can use and further create value. So for example, real-time reporting of where construction zones are or where there is traffic congestion. How value over and above the value of just moving a person from place to place. And so don't get me wrong, the hardware is an essential start to this overall process. But really the business value is embodied in all of those things. And the information and services are from our modeling, frequently more valuable than the hardware business itself. So let's talk a little bit about where the compute happens. So if I look back the last couple of decades, a lot of it has been creating the cloud. Large data centers, hyperscale data centers, distributed data centers, where really the job was to collect information at the edge, funnel it along multiple pathways, and bring the data to large scale mass market compute. Make a decision, whether that is just rolling it up or actually acting on individual pieces directly, and then sending a simpler thing back to the edge that requested it. As we look going forward, because the volume of the data being created everywhere in this network continues to rise, we expect that the compute will begin to disaggregate and move elsewhere within the network. What we call this generically is distributed connected compute. What we want to do is bring the compute to where the data is created. And as I said on the previous page, it adds quality of service, it adds security. In some cases, there are privacy rules. But that amount of compute will be different than the essentially mass market compute that is in the hyperscaled data centers. So what drives validation? Very, very simplistically, you might think of the task as, well, you design a chip, you validate the chip. However, of course, there's always a package that goes around with it. In the old days, you could treat these as kind of separate tasks and not think very much about that. Clearly, the systems that we build today are far more complicated, and so it's not enough to validate a chip or a package. You really need to validate the system design and the how it operates together. But that's just the starting point. If you think about it from a data point of view, there's really a wrapper around here, which is software and the data flow. And the boundary of where the validation ends is now deliberately blurred. It's defining where is the boundary of the system from a standpoint of making sure that it operates correctly, that it is resilient to failure, and that it really does what people expect it to do. If we look at some of the details about how people are implementing compute in this new world, starting on left, this is a phone SoC example. This particular one is from Apple. If you look at the die, what people tend to focus on are the blocks marked in yellow and orange, which in this case are the GPU and the CPU. And they spend a lot of time thinking about benchmarking and other things of that. But if you look at the bulk of the chip, a great deal of the chip is made up of multiple unlabeled blocks. Many of those blocks are special purpose processing units for audio, for video, for photography, for communication protocols, etc. Each of those is a specialized function and has to work as an overall system to make the compute happen. And as you can tell from the area of the photo, a lot of it is devoted to that, and much less is going to the general purpose compute that is elsewhere. Now, this is an edge example and a monolithic example. In the center of the page, this particular example is from Google. There are application-specific processors. In this case, TensorFlow is an application, and the TPU, or tensor processing unit, is this custom architecture to process that. And what they find with custom architectures is there's a speed up of anywhere from 10x to 1000x, depending on the details along the way. We can afford to do that because of the sheer volume of data. You wouldn't necessarily build a custom processor unit if you weren't overwhelmed with a particular kind of data. And many other companies have been doing similar things. On the right-hand side of the page are some examples of things that are either related to AI or communication processing or other things, but they're enabled from an economic point of view by the sheer volume of data, and therefore the opportunity to do this faster and better. Now, how do you implement it? In the previous page, I had a monolithic example and I have a disaggregated example. For each time you define a new architecture, you have to make that choice. So perhaps you start with a new application. You figure out what the domain specific language might be. You know, essentially, how are you going to program that architecture? You work out the architecture that is optimal for that particular task. And now you're going to build a hardware engine. In this particular example, I've built essentially a general purpose machine next to a custom machine, because frequently you find that as an application, while the difficult part or the time intensive part may be custom, there is frequently a lot of general purpose stuff around there going on. In this particular case, I put two chips in the same package with a bus between it. You can then say, now let's consider that going forward, and you can create things like the diagram on the right, where you have I/O separated from memory, separated from general purpose compute. If you do this the right way, you can simplify the design. You can make each of those chiplets now more regular, easier to validate, reusable design perhaps. In some cases, you can improve yield. If you do it right, you can also reduce the time to market, the time to bring the product to worthiness to sell for revenue. Now, if you don't do it right, you've cut it in the wrong place. You've created difficult to validate interfaces. And the validation now has to happen across the whole system, even if you can subdivide the task along the way. So again, returning to the emerging complexity, on the left is simply the complexity of doing the design. There is a corresponding example in the programming world. If we create a heterogeneous architecture with a lot of essentially hidden optimizations within it, then it becomes very difficult for a programmer to extract performance. In the early days of software, you basically had to know the hardware inside and out to be a programmer. Today, we have many, many more programmers, but they're used to working at a more abstract level. And they typically can't figure out where these optimizations can occur. And so we bring compute to bear. The right-hand side is an example of some automated tuning publications, looking at, can we automate the optimization of code so that a programmer doesn't have to deal with the problem in the middle of the page. The same thing occurs for a problem in the EDA industry, or a problem within the, how do you write code to do validation? And we have other technical barriers that we have to deal with as well. So the problem of data moving around is very energy intensive. So the left-hand side is an example of the power efficiency versus what we would like it to be to get a certain amount of bandwidth. The middle is an example of, you've created so much data, you really don't want to fill up the network with it. And so it's a driver for doing local processing of information and sending a much reduced set back to wherever you need to do. And then the right-hand example is an I/O chip power problem where, again, trying to achieve a certain amount of bandwidth is consuming an ever larger portion of the power budget. It is not unusual today to look at within any system and find that a third of the power is going simply to moving the data around, leaving much less available for compute. And then finally, we can't ignore the fact that there are active adversaries in the world that are either in it for money. Ransomware is an example. They're in it to collect information, the espionage. And so finding ways to ensure privacy and security as we distribute the data, as we distribute the compute, is an ongoing problem. And I refer to this as different than fighting the laws of physics. You can wake up the next day and realize the laws of physics haven't changed, but you may wake up the next day and realize people have figured out a new way to do a particular attack. So now let me talk a little bit about technology trends that are sort of the foundation of this. And I typically talk about it in three buckets. Down the center of the page is Moore's law and the technology required to make it keep going. On the left and the right are the product and the workload optimization that I talked about a little bit earlier, and the product and process co-optimization that I talked about as more and more important going forward. But let me start in the middle of the page. So on the diagram that I showed from 10 years ago, we already were talking about the thing in the middle of the page, the nanoribbon or nanowire type approach. It is a continuation of the move into 3D. With the FinFET, we extended the transistor in the vertical direction, and then we basically cut that into pieces and do that as nanoribbons. Now, we do that because it improves the overall characteristics of the transistor. The diagram on the right-hand side is drive current. That improves overall performance per unit area. But you can see from this particular diagram, there isn't a density improvement. There's not a change to the physical footprint of the transistor. It's just a better performing transistor. If I take and I stack two kinds of transistors on top of one another, though, I now start to get a density benefit. In this particular case, we have an NMOS and a PMOS that are made out of different materials. We stack them on top of one another. There's interconnections that are essentially vertical to connect them. And we see a density benefit as well as, in this case, a performance benefit because we've optimized the materials for the particular device that we're trying to build. If I look a little bit into the future, I can continue this model and say, well, what if I start stacking up either fins or nanowires together, and perhaps I make them out of different materials, or I optimize them otherwise. What I can do is create both performance improvement as well as a density improvement, and I can keep the equivalent of the economics of Moore's law going a lot further. And this is really where we expect things to go. And the memory world has already done this. So some NAND flashes up to more than 100 different layers of stacked devices along the way. Think about this though from a validation point of view. You've created this complex circuit that's interconnected among the greens and the reds, and you find a bug and you say, well, how am I going to figure out from a physical nature what's going on there? So this is an example of some of the complexity that we will be creating with the future process roadmap. And interconnects are similar. We have been mostly keeping up with interconnects by shrinking the pitch and adding more layers, as shown on the left. As we go to disaggregated design, we're going to have a complex interconnected architecture at the package and the die level. And this is creating a dense 3D wiring opportunity, but it's also a challenge from an interconnect, from a debug point of view. And around the corner, we have other novel architectures. This is an example where we take the conventional die architecture and we split it into two pieces. We have the transistors in the middle, and we bring in wires from both sides. In this particular case, I brought signals from one side, power from the other. There are other different variations that you can imagine. Addressing wiring and power delivery is an important part of keeping the performance benefits going. So now let me shift gears and talk a little bit about the right-hand side of the diagram. So the product and process co-optimization. So what we see with the rise of large sets of unstructured data is there's really a massive compute demand. They are highly parallel workloads. They demand high bandwidth memory, far larger than what we're used to do with a CPU type workload. We would like larger systems, and in many cases, we want them to be larger than what the reticle can hold. And there, as I talked about, new system architectures along the way. Further, we'd like to be agile because as we collect new kinds of data, we find frequently the architecture needs to be tuned along the way. What that tends to imply is that a single process choice is probably not optimal. We may need to have a very high density, low power, highly parallel set of transistors to process, let's say graphics, for example, but a higher current, higher frequency set of transistors to drive analog, RF, and so forth. Figuring out a way from a process point of view to make an all-in-one process is increasingly both expensive and difficult. And so going to an architecture where we've disaggregated pieces and within a piece we can be more uniform, that's an important part of making this going forward. Now, having done that, we potentially create a different problem. We create interfaces. And by doing things like this, we may want to have a high density interface in one place and a lower density interface in another place for the same reasons we wanted high density transistors in one place and low density in another. The optimization problem is different for different places. And so we can continue to shrink things at the package level, continue to have higher density things. But again, we're adding more complexity along the way. We perhaps can create better power delivery and higher bandwidth interconnects, but from a system architecture point of view, we're making it more complicated. Again, we can continue to densify. We need to think about metrics that are beyond simply one-dimensional wiring pitch, but thinking about the equivalent of how many I/O units there are per unit area and per 3D volume. We will have to do new materials along the way in order to enable part of that. But that future is already here. So we're already shipping products with architectures like this, and we'll be shipping more products like this going forward. So starting on the left, our FPGAs have I/O chips, they have a high bandwidth memory, and of course they have the FPGA. They are a mix and match architecture. DARPA has a project looking at whether we can create an ecosystem that allows people to essentially build into this particular platform. Lakefield on the right-hand side is a different implementation. Here it's a face-to-face, die-to-die stacking with other packaging around the outside. It gives us a very small footprint and enables different form factors for PCs. This gives us opportunity to reuse design, opportunity to have interoperable pieces of this, but it also requires the system technology co-optimization, now beyond the design technology co-optimization that we have underway. And we expect that this trend will continue as well. And here's some of the numerics around bump pitch and bump density, as well as the power in terms of picojoules per bit. So what's that mean from a product and a workload co-optimization point of view? First, these are complex. And when you have complexity, you have to deal with it, because an exponentially increasing complexity problem means you either need an exponentially increasing budget, which none of us have, or you have to find new ways to do things. And generically, there are three specific areas that people have focused on. One is to essentially partition the design. So making it into modules, whether those modules are chiplets or whether they are blocks within a monolithic design, but also refactoring. To paraphrase a famous physicist, interfaces are created by the devil. If you create the interface in the right place, you simplify the challenge. If you create the interface in the wrong place, you've made your life hell. The nature of interfaces is that they have to be standardized, they have to be formalized, so that you can verify the interface independently from the operation within the overall building block. There are a lot of examples. I'm not going to run through the list that I have on the page, but there's a lot of examples of how to properly refactor a design, how to make it simpler both to design, to validate, to debug once it's out and operating. The next thing that we do, and this is already happening in the programmer world, is that we create layers and abstraction. Now, what we're doing is essentially hiding complexity from a layer up above. And so there's a risk here as well. If you create the layers in the wrong place, you've made your life worse, or you can't take performance and get it out of your system. And so the third piece, of course, is finding ways to automate much of the complexity of the task along the way. That may be making it faster to design, it may be faster to program, it may be tuning along the way. All three things we have to bring to bear in order to handle the complexity that we're creating along the way. So from a design productivity on the left, defining it starting from the software is one example of ways to do that. We potentially, of course, are making our life easier from a hardware point of view, but harder from a software point of view. One of the things that we have to do is do rapid exploration around different kinds of software, different choices for architecture, microarchitecture, as well as physical design, rather than starting from the other way around, doing a physical design, figuring out how to optimally program it, figuring out how to make it run very well from a software point of view. There are many different techniques that are involved. I think all of them will need to be brought to bear on this particular thing. And again, if we just stopped at creating these different pieces, then we're potentially creating a higher complexity downstream. And so if we look at programmer productivity. The left example is simply a made-up example of how much the code bloats as you go to higher and higher levels of abstraction, going from essentially assembly language on the left to writing in Python on the right. From a programmer point of view, though, the people that are familiar with the things on the right vastly outnumber the people that are familiar on the left. And so we need to deal with a programmer world where most programmers will operate with a high level of abstraction. And we need to find automated ways to move the performance down into the stack, whether that is generation of code, whether it is being hardware aware optimization, or whether it's simply trying to figure out what the programmer meant to do and figuring out more optimal ways to implement that. Again, we're going to have to bring all of these methods to bear. And then what about validation? So here's an example of the runtime various design phases, and using that complexity of a heterogeneous system and getting 3x faster throughput with optimizations of spreading the workload across CPUs, GPUs, in some cases ASICs and FPGAs. So again, while Moore's law creates complexity, Moore's law products can help us deal with that complexity. And what people are finding is if, excuse me, if you throw a lot of compute at a problem in a right way, you often find unexpected benefits better than what an expert has been able to achieve. So the rise of AI was really around unstructured data, not for the kind of data that we have in chip design. But what we're finding is that discovering essentially a better optimization point can be done with brute force. It's like the early days of chess programs where you just look at a lot of different moves and you pick the best one. In this case, it takes a lot more compute to make this work, but you get smaller block area, you get better performance along the way. But I want to come back to validation and think about what it means to detect an error. Let's imagine we're building a product. We do a certain amount of internal validation, and then we're ready to ship. Well, we're in a mass market business, so we're obviously going to ship a lot more systems than we've ever validated. That's the nature of mass market. And so the large customers in the world will exercise a lot more cycles than we have been able to do. We all have known for a long time that our products are more complex than we can exhaustively test and validate. And so it's quite possible that a large customer can find things that you could not detect from a validation point of view simply because of the number of cycles. Now, imagine a hyperscaled system where you put all of these compute in the same place. Now, suddenly, your detection capability has gone up as well. I raise this not to say that this is a problem that's insurmountable, but the problem means that we have to move away from thinking that we can prove everything at time zero, prove everything in the lab. And we need to get to a point where we can prove resiliency and reliability at scale. And so again, part of this is figuring out how to modularize the problem. Part of it is figuring out how to extract the problem. But part of it is figuring out automated ways to handle errors along the way. Because if you think about it, just from a number of cycles point of view, something might take years to find in the lab, weeks and months at a large enterprise customer, but simply hours within a hyperscale business. So back to verification. If I think about how we might have done verification a couple of decades ago, as I said, there's a chip design and a chip verification that might be independent of the package. The package design comes sequentially after doing the chip design. There's an equivalent verification. Once the packaging is done, there's a system design, and finally a system verification. In this new world, we're going to have to do a lot more co-optimization across all these elements. So we need to view the system as the whole, the system including the software and the data. We need to think about the system architectures for how they're going to handle that, and where the cut lines are, where the abstraction has to occur. And the designs of the system, the package, and the chip may go in the opposite order and need to integrate and iterate together. And the same thing is true around the verification task. Now, key messages here. Data into information is really what's going to be driving the next decade of compute. So we need to think differently than we've done before. Moore's law can continue. We will continue to do some amount of two-dimensional scaling, but a lot more of it will go into 3 dimensions. A lot more of it will come from design co-optimization and novel integration. 3D ICs have the possibility of creating compelling products, but they will also create new challenges and complexity in design and verification. So thank you, and I'll open it up for questions.
It looks like there is one question listed in that Q&A box, if you can see that at the bottom of the menu.
No, I can't. I can't see it. Sorry. Let me stop sharing here. Q&A. There we go. Is Intel planning to move from the hardware space into the service and information space, given the business value? Yes, but selectively. We have Mobileye as an example, and that was the one that I used here. We have some others that we are incubating at the moment. Mobileye, when we acquired them, was largely a hardware company. They've rapidly expanded their capability. They had been thinking along the lines before we acquired them. But as we look at what our customers are needing, they're needing more in the way of overall optimization of the problem. And if we are able to optimize and add value for the customer, then it's possible that we can capture at least a fraction of that overall total. I don't expect that Intel will rapidly become a service company, but it is something that will add to what we've been doing along our historical path.
So let it also open up for any live questions. So in case you want to ask directly a question, you can unmute yourself and use opportunity for getting a question. So first of all, thanks, Mike, for this really detailed and excellent keynote. Usually we would now get a big applause in the room. It's a bit difficult to do this, but we give you our virtual applause on that. And yeah, so let me look around in the room if there are any additional questions related to your keynote. So if people are still thinking about one, I had one also with the other keynotes from Vicky and Moshe on the software side, because they were hinting a lot to what can we learn from the software world into the hardware development side. And if you could elaborate a bit how this system thinking is changing based on the previously hardware separated, software separated, now going ahead in a more system thinking, also to keep the Moore's law alive in that context. What is your view on this?
Yeah, I think there is a lot to learn across domains. I think in some sense, agile hardware design is inspired by some of the rapid software design methods that people have done along the way. I think the notion of how do we formalize interfaces could benefit from some of the thinking around modularizing software. I think the one of the areas that we're exploring, but we don't have quite an answer to, is are there better ways to assess risk, whether the risk is in the verification, whether the risk is in the development. There have been a lot of bodies of work around assessment of risk in software. Long ago, I forget how many decades ago, software Keynote basically said the reason we do testing is to know whether to ship, not because we think we can find all the possible bugs. There may be things that we can learn from a standpoint of when do we think we can assess the confidence level by repurposing message from software. So yes, I do think there's a lot to be learned along the way.
All right. Thanks. I think meantime also more questions coming up.
Let's see. Do you think we should focus on optimization of current designs, or is it a good idea to continue exploring how to improve the technologies? It's really both. And so I'll tell again an old story. There used to be this software spiral. You'd build fast hardware and then they would write bloated code and it would slow down, and then you build faster hardware. Well, we don't necessarily have the luxury to just say, hey, take your code and make the underlying engine go faster and run it without modification. Now, with abstraction, you can do that to some extent, but finding ways to tune the software to the hardware is an important part of it. So I think we have to do both the improve current designs, but also look at co-optimizing between I'll say simplistically, the workload, to distinguish between just the software component, the workload, and the overall hardware. Right. Let's see. Seems that shrinking process nodes is increasingly difficult. Given that process yields are decreasing, could we consider incorporating more programmable chips for consumer use? They could be programmed in order to cope with silicon defects. Yeah, so let me answer that. Yields have not necessarily been decreasing, but there are certainly more kinds of failure modes that you have to worry about simply because you have more layers and more complexity in the process along the way. If you normalize on a per feature basis, the yields are actually continuing to improve, but you don't care about that. You compare about what happens at the full chip level. And increasingly, as we realize that we can never fully test, the possibility of escapes becomes an important part of that. The shrinking is difficult, yes, and it's a lot of work, but it's sort of a one-time thing. Whereas doing a new product on even an existing node, you run the possibility that you created a hole in terms of how you test or how you verify. You perhaps uncover a different marginality between the design and the process that you didn't realize that you have. So resiliency in a general sense, I think, is an important part of this. We've already, of course, had resiliency from a standpoint of error checking in memories. FPGAs are one way to program around detectable things. But I want to point out that it's not just the time zero problem. It's also, what if you didn't detect something along the way? How do you detect it when it's already running in the field and how do you make sure that the result remains reliable along the way. I talked to a reliability crowd earlier this year and made that key point. So yes, I think FPGAs are one way to do that. I think they're not the only way that we need to approach this particular problem.
All right, then I think another one for Moshe. Thanks, Moshe, for asking that question. So it's about improving productivity by starting from the software down to the physical design. Can you add more details about this?
Yeah, so today, actually, I'm not sure if this number is precisely accurate, but the amount of money spent on software dwarfs the amount of money spent by hardware by about 5x. I think that's about the right bottleneck. Ballpark number. Mm-hmm. And so, from a productivity point of view, working on the software side of things has more opportunity. Making the programmer life easier has more opportunity. At the same time, you may be creating a performance bottleneck. You may be creating a different kind of problem at the hardware level. Now, if you're doing hardware design, if you narrow the problem of what you need to deliver, then finding the optimal implementation of the architecture and the microarchitecture becomes simpler. And so going to a hardware architecture where you have a lot of simpler building blocks is a way to improve hardware productivity as well. Again, you have to do it correctly. If you just run it through a meat grinder where you cut your interfaces, then it's not going to be any easier. And so I'll return back to the point that I made earlier, that formalizing what those interfaces look like, formalizing what the handoff between the different pieces of software looks like, formalizing the abstraction between layers is an important part of making this work. But at the end of the day, somebody's going to have to do real work, whether it's coding, whether it is microcoding, whether it is actually designing and verifying along the way. So there's no getting away from the total amount of complexity, but you can manage that complexity in probably more efficient ways than we've done so up to this point in time. And because the complexity continues to grow, it's not a one and done. You can't just say, okay, I've now the next method that I'm going to use for the next 10 years. It's something that you have to continue to improve along the way.
All right. Thank you. And next question is a very interesting one from Lucas. How much do you think is left in physical optimization? I guess this question you get since 84, 95, and 2005, and 2015. So I guess this question is on since quite a while.
Yeah, there have been, of course, different answers to that over time. When I started, Moore's law was going to end because we couldn't print smaller than the wavelength of light, and then we figured out how to build masks that would surpass that limit, and then we couldn't build devices that wouldn't leak, and high-K metal gate and tri-gate are examples of way to get past that. And then there's the whole two-dimensional process control, and again, we're getting past that by moving into the third dimension. It is true that any particular path will eventually have diminishing returns, and 2D scaling is indeed one of those. But from a 3D scaling, the barrier is more economic. If you put more layers and you don't figure out how to do it cleverly, you just keep adding costs. And Moore's law, among other things, is around economics. So I think we can continue, and I've learned that I basically say we have about 10 years of visibility, and there's fog beyond that point. 10 years ago, I said, well, we can't see past 2020. Here we are in the year 2020, and we can see further down the road from here. I happen to be retiring this year, so it won't be up to me, but I have confidence that the people that come after me and have been working with me will continue to push back that fog.
Thank you a lot. Then a couple of more questions coming in from Paul. Is Intel working on new higher level programming languages to enable programmers' productivity using these hardware trends?
Clarify that. I didn't quite understand what that meant.
Maybe, Paul, if you can unmute yourself, that you. Let's move to the next one, unless there's a further clarification on that question from Daniel Grosse. Do you think that open source principle, which now seems to come to the hardware world, RISC-V open source tool will have impact?
I'm going to say perhaps. I think that certainly open source has been a good way to have more, I'll say, eyes looking at a particular problem, and just like the compute example, more wetware compute cycles often gets to a better answer than simply one person thinking about it. I think from a hardware point of view, some things would get better. So scrutinizing for let's say security holes is one of the promises of it. But the possible downside is that, a horse designed by committee is a camel. Hardware designed by committee is potentially good for a lot of things, but not great at any one thing. I think we'll have to see how it plays out. I certainly see a role for open source around things that we can all agree and standardize. Standard bodies are an example of that. But how do you optimize one thing for one task? That may not be suitable to work by committee. We'll have to see how that goes.
All right, thank you. Let's see. Any more questions? In case Paul can come online, then you could clarify your question. Else, I think we have time for one more. Yes. Thanks, Paul. So the presentation said that the most programmers are working at a higher level, e.g. like Python, and there seemed to be a problem around translating that intent into the hardware.
Yes, so it's a problem that people have struggled with. Part of it is related to the design of the language. If you make a language more constricted, then it's easier to figure out what the task is, and then automate the next steps to get high productivity code. But humans don't like constraints. They don't like to be too narrow, and so it's always been a trade-off from a design of a language about how general purpose you make it. I think the fact that people have had great success with things like halide to narrow the domain down enough. And halide is an example where you basically separate the intent from the implementation, and then you automate the implementation. As more of those things become available, I think people will start to appreciate them more. TensorFlow is an example. It's not perfect, of course, but where it's designed to allow the data scientists, not the programmers, the data scientists to think about the flow of the data. And in a sense, it is now then separated from the implementation step. And so I think there are potentially ways to now that you've abstracted the layer between the first and the second piece, to now figure out how to do a better job further down the stack. That is being worked on. It's certainly not done yet, or at least not done to the satisfaction of the people that have to deal with large volumes of data.
All right, probably one last question. As the trend is applying from Dugmin now, as the trend is applying for machine learning algorithms, which is opening several vulnerabilities. What do you think about building security into the hardware?
So we already know that many of the AI systems are easily fooled. I mean, humans are fooled. You can think of optical illusions as an example of it, but they're fooled in ways that you wouldn't expect from a human point of view. And so we have active research around how do you detect essentially the window, the security window that you have within an AI system. How do you make sure that the system is bounded? And some work around, I'll say, after the fact explanation of why did it behave the way you did. Now, obviously, you'd like to avoid all of these things in the first place. But as a practical matter, just like the verification problem, we won't be able to completely verify our AI systems. So we have to put other things around the outside. I think that I'll return to the point that I made earlier. The adversaries are active and they're learning. And so it's something that we need to be working on essentially constantly, not just assume that we can build a robust system and then it will always be secure. But be paranoid to think about what the kinds of attacks are. You know, as we make more complex systems, we are potentially making it harder to verify from a security point of view along the way. It's a tough problem. It's tough because the adversaries are active.
All right. Thank you a lot, Mike. Time is over, and thanks again, for a fantastic keynote, for answering all the questions. And one thing about this whole virtual setup, we have lots of attendance from US today, from Asia, and also even one from Australia, besides the ones in Europe. So thanks for giving us a keynote, and yeah, looking forward to hopefully see you soon in Munich.